All right, welcome everybody. Let's get started. My board seems to, I'm really sorry, I need to put my screen up here. Easier to view my board. Yeah, all right, let's pin my video. Great, yes, okay, I'm still a little blurry. It's weird. All right, I wonder what that's about. Let me see if the camera might be a little smudged here. One sec, sorry. Okay. No, that doesn't look any better. All right. So, a couple things before we get going. Just want to remind everybody to do the quiz today. It's on Canvas. There should be a link to it. There's like 3 or 4 questions, I believe, and to submit it on Gradescope. Hopefully that all goes as smoothly as I imagine it will, but I don't actually know. So if any of you encounter any trouble submitting your quiz on Gradescope, just let me know and we'll try and get it worked out. If worse comes to worse, I'll just have you guys email it to me. But the idea, hopefully, is to have you submit it to Gradescope. The second thing is to make sure you fill out your weekly participation log. That's also should be done today. That's a Google assignment. So if you go there, yes, the quiz is due tonight by midnight. It shouldn't take you too long. It's not meant to be super duper hard. It's just meant for everybody to get a chance to kind of do some practice and for me to give you some feedback on how well you're understanding the material. Sure, we can go over one of the questions in the quiz if you want. Which one? Oh, sure. So let's go ahead and take a look at that. One sec, let me grab the quiz for myself. Quizzes. 1 second here. So I also, hopefully that link actually works. Let's take a look and see. Sorry, 1 sec. Cool, totally works. All right, so I'm gonna share my screen with us for a second. Now let's share my screen. Okay, so if you look at my screen here, you can see the quiz on the right-hand side, and it says, here's the function, and what's the range of this function. So if we look at the function that's graphed in Desmos here, so it's, and here's how you, if you want to like restrict the domain of the function, the way you do it is you put the restricted domain in little braces like this. So it's negative x plus 2 squared when x is less than negative 1, x plus 2 when x is between negative 1 and 3 inclusive, and it's 2 to the x minus 3 when x is larger than 3. So we can kind of follow the graph here, right? We can plot points, and we can see that you don't quite get the point negative 1, right? It's not quite there. And then we do get the point negative 1, 1, 0, 2, so on and so forth. And it looks like the only, so I don't want to really kind of say all the entire answer, but it looks like the range goes all the way from negative infinity up to 0, right? All the y values go from negative infinity to 0. And we're missing the y values between 0 and 1, but then we have all the y values from positive 1 up to forever and ever and ever to infinity. So that's what I would say about that. I wish I could see the chat when I share my screen. At least I don't know how. Maybe I'm just not that smart at the zooming. Yeah, I don't know. So anyway, that's what I'll say about the quiz there. So if you look at the graph there, it should be able to see what the range is. And if you're chatting at me, I don't know how to see it. Oh, maybe I can do that. Oh, cool. Yeah, there's a chat. Awesome. Great. So again, I'm happy to go over quiz things with you, but again, I want you guys to realize that you're not really graded on this quiz. Like, I'm going to grade it and give you feedback, but getting it all right isn't super duper important. Doing it and then getting feedback is what's important. So I'll talk about 1B, but I really want you to kind of think about this is stuff I want you guys to kind of try and do on your own, because that way I can then kind of help you figure out where you might need to work on it. So here's what I'll say about, so I'm not going to finish it, but I'm going to say this. So I'll do a different problem actually. How about that? So let's say I want to find, oops. So let me stop sharing my screen so that you can see what I'm doing over here. Awesome, great. So let's say, my room just got warm. All right, chair, move on over. So let's say we had f of x equal to the natural log of x plus 1 to the 4th times x minus 2 cubed times x minus 5. And I'm trying to find the domain of this function. So for any logarithmic function, we're going to say the following. We're going to say, okay, the inside stuff so all the stuff inside the logarithm has to be strictly greater than 0. Right? We can't take the log of 0. We can't take the log of negative numbers. So then the way I usually tackle a problem like this is by finding the zeros. So the zeros of this left-hand side of the equation are x equal to -1, +2, and +5. And then you plot this on the number line. They happen to be in order. And then you want to see what the sign of this expression is in each of these 4 different intervals. So if I pick a number larger than 5, like 6, this part's positive, this part's positive, and this part's positive. The product is positive. If I pick a number between 2 and 5, like 3, this is still positive, this is still positive, but this now is negative. Since to an odd power it stays negative, so the overall sign is negative. You also, instead of doing that, could have said, oh, well, 5 came from this factor. This factor has an odd power of 1, meaning the sign is going to change. In a similar way, this 2 comes from this factor with a power of 3 that's also odd. The sign is going to change again. You could also see that by picking a pointer. If you pick 0, which is between -1 and 2, and plug it in, this part's positive, this part's negative, this part's negative, and a positive turns to negative turns to negative is positive. Finally, when we go from this side of -1 to this side of -1, you can either say the sign is going to stay the same because -1 came from this factor that has an even power, or you can pick a point like -2 and plug it in. If you plug in -2, this part's negative, but it's to an even power, so it actually ends up being positive. This part's negative, right? -2 minus 2 is -4. To an odd power stays negative. And -2 minus 5 is also negative. So it's still positive times negative, which is positive overall. And then we want it to be greater than 0. So we want the positive parts. We don't include the endpoints because we can't take the logarithm of 0, right? This is strictly greater than 0, not greater than or equal to 0. If this was a square root, like if it was f of x equal to the square root of all this stuff, then we'd have greater than or equal to 0, and we'd include all the endpoints. So our domain here is going to be everything from -infinity to -1, union -1 to 2, union 5 to infinity. And I thought, so we changed the charge, or I'd say we changed the sign. Yeah, we changed the sign of the charge when the power is odd, and we leave it the same when it's even. That's exactly right. By the way, now that it looks like just about everybody's here, if everybody could please go to this link and make sure you fill out your student ID number so I can record your attendance. That's why I decided to do it now. The other thing I was doing wasn't really working so great. So if everybody could please go do that before the end of class right away. It should take just a moment to do and be fairly simple and straightforward. Let's see. I know there were some other questions, so I was looking through your guys' various responses to different things. This chair is just in the way. Let's move the chair. Also, feel free to turn on your video, say words. It'd be great. You don't have to, but you're welcome to. So let's see, there was a couple other things. Somebody asked somewhere, essentially, sorry, someone's just, sorry, one sec, apologies. Looks like someone's trying to join the class. Okay, sure. We'll get back to that later. All right, so someone asked something like, why does the natural log of e to the 2x minus 1 equal 2x minus 1? It's a really good question. It's kind of an important question because we use logarithms a fair amount in this class, and it's important to kind of understand how they work. So here's kind of where I started thinking about this. So what does log base 2 of 8 actually mean? Right, I need to mirror my screen so that the numbers don't look weird to me. Sorry, one sec. Video settings. I need to unmirror my screen. You need to be looking good. All right, so what does log base 2 of 8 really mean? Well, when I read this, what I see this as meaning is this says 2 raised to what power equals 8? That's the question this is asking. So 2 raised to what power equals 8? Well, it's 3. Now, and write this 2 to the third equals 8. Another way you could write this is log base 2 of 2 to the third. Right, 2 to the third is equal to 8. So when I read this, it's going to sound kind of dumb, but I'm going to ask the question, 2 to what power equals 2 to the third power? Well, the answer I think is pretty obvious. It's still 3. Right? When I read this, this says 2 to what power equals 2 to the third power? Well, clearly the power there has to be 3 so that these two things are equal. In a similar way, and again, these are going to seem kind of dumb, I think, but I think they're worthwhile. What if I said log base 5 of 5 squared? What's log base 5 of 5 squared? Everybody. And I think I've got my volume turned up so I can actually hear you say things.
2.
Definitely 2. Because 5 to the second power equals 5 to the second power. You could also, you could write it differently. You could say log base 5 of 25, but it's still the same thing. 5 to the second power equals 25. And this is the same for anything where the base here is the same as the base here. If I said log base 3 of 3 to the 4th, what's log base 3 of 3 to the 4th have to be?
4.
Yeah, 4, exactly. Because again, you're asking 3 raised to what power equals 3 raised to the 4th power? Well, the answer is in the question. We've already said it. Now, that's also what's happening here. The thing is, it's just the notation is slightly different. So when I write natural log of e, in fact, let me actually just give you guys a good one. So when I write, say, like the natural log of e cubed, we write it this way because we want to save time and space, but really this is just an abbreviation for the log base e of e cubed. So what's the log base e of e cubed, or e to what power equals e to the third power?
3.
It's got to be 3. There's no other choice. So that's what's really happening here. So when I write this, nope, dropping things. Sorry. When I write this, what I'm really thinking of writing is log base e of e to the 2x minus 1. So what that is asking me for is e raised to what power equals e raised to the 2x minus 1 power? And the answer has to be 2x minus 1. Now, that's always true. So what we're saying more generally here, and think about this to the other side, is that log base b of b to some power is always just going to equal that power. Or if you want your base to specifically be e, you can either say log base e of e to some power is equal to that power. Or the more normal way, the natural log of e to some power is equal to just that power. That's what's going on there. Yeah. The questions about this. Okay. I'm going back to the other side, actually. So there were some other questions that were submitted, brought up, which I should address. Someone was asking, a couple of you actually were asking about the transformations that Sanders was talking about in class on Friday. And there was one specific that was a little challenging. So we're going to look at some similar examples. So let's look at how to graph the function, say, f of x equal to the natural log of negative x plus 2. This isn't exactly the same one that he did. He had some other pieces to it, but this is kind of the important part here. This one has a horizontal shift and a horizontal reflection. And the challenging part here, let's get some more light. Yeah, sorry. The challenging part here is that these can always seem kind of backwards. So here's how I would mostly encourage you guys to do this. So this is going to feel wrong, but maybe. But this plus 2, so again, when you add on the inside of the function, that's going to shift it to the left. So this is going to shift us left 2. So I'm going to actually draw the 3 graphs. I'm going to draw y equal to the natural log of x first, which is my usual natural log of x function with the y-intercept with x-intercept with 1, 0. And then this is going to shift it left 2. So the graphs are a little too big. I want to fit all 3 of them in. Let me just make this a little smaller. Sure. Okay, great. So then we're going to do y equal to the natural log of x plus 2. Right, just doing the left 2 part. So my vertical asymptote, which was at 0, x equals 0, right? That's my vertical asymptote. Now my vertical asymptote is going to shift 2 to the left. And my y-intercept, or sorry, my x-intercept is also going to shift 2 to the left. It's going to be shift from 1 to 1 minus 2 is negative 1. And it's going to look like this. Okay. And now we're going to do the reflection. So this negative here is going to reflect us about the y-axis. So what ends up happening is this whole thing flips around this line. So this part this point stays stationary, but now this part is going to be going that way, and this part is going to be going that way. So importantly, my vertical asymptote flips from x equals negative 2 over to x equals positive 2. So it looks like this. So if you have a horizontal reflection and a horizontal shift, I think the easiest way to do it is to do the horizontal shift first. So this shifts 2 to the left like we normally would, but then after you do the reflection, it actually looks like you shifted 2 to the right, but you also have the reflection. So it can be kind of weird. There are other ways to do this, but I feel like this is the most consistent way to do it correctly. Yeah. So let's look at another example. Where'd you go? Other example? Sure. And so actually one more thing to say about this. So in case you're not kind of convinced, or maybe, if you look at the domain of this function, right, we know the domain for a logarithmic function is, well, the inside stuff has to be greater than 0. The easiest way for me to solve this inequality is just to add x to both sides. If I add x, I get 2 on the left is bigger than x. So this says my domain is x is less than 2. which is definitely what this looks like, right? I've got x equal to 2. I've got everything less than 2. So we can also see that the domain makes sense. Yeah, we're definitely going to get to log, and semi-log. I just wanted to cover this stuff, and that was what was next on my plate. For anyone who just came in, I want to make sure you fill out the attendance on the. Oops, that's not what I wanted to put in there. Sorry, apologies. How did that come up? That was something else that wasn't as useful as I wanted it to be. There we go. There's the second link there is the link to the Google Doc for attendance. Please go there and fill out your student ID number and which class this is. Let's do one, maybe 2 more examples of this. And then we'll talk about log, and semi-log. So, in fact, why don't you guys try graphing this one? So try graphing f of x equal to the square root of negative x. Now, what did I do there? Minus 4. So again, I think you should do the shift first. It's going to shift. Well, I don't want to give it away. I'm going to give you guys a minute. It's going to shift in one direction, either left or right, and then it's going to give you a horizontal flip after that. Actually, I really need to use the restroom. Perfect time. You guys work on that for a minute. I'm going to go use the restroom real quick. Okay, so here is what I'm seeing from this problem. I've got a shift to the right of 4, and then I'm going to have a horizontal reflection. So looking at the 3 graphs, here's the parent graph, y equal to the square root of x. And it's got this usual shape to the point 0, 0, and 1, 1, and 4, 2, et cetera, et cetera, et cetera. And then I'm going to go 4 to the left. Sorry, 4 to the right. I apologize. So I'm going to go 1, 2, 3, 4 to the right. And this is the graph of the square root of x minus 4 without doing the horizontal reflection yet. But then I'm going to take this and I'm going to reflect it all the way around the y-axis. The other way to think about reflecting around the y-axis is basically all the y values stay the same, but the x values become the negatives of what they were. So instead of getting 4, 0, I'm going to get negative 4, 0. Instead of getting 5, 1, I'm going to get negative 5, 1, and so on. So my final graph here, the square root of negative x minus 4, starts at negative 4 and goes that way. It's got the point negative 4, 0, and negative 5, 1. So hopefully that clears up the horizontal reflection and shifting kind of issue. If you do the shift first in the way you think it should be, and then do the reflection after that, it should always work out correctly. But again, I know the end result looks like instead of shifting to the right, we actually shifted to the left. And that's kind of true. But if you do it this way, you will figure it out. You'll get there the right way this way. All right, let's talk about some log, and semi-log stuff. I don't want to do, well, that's not true. I want to do tons on it, but I feel like this textbook, as compared to the previous textbook, doesn't spend as much time talking about the log and semi-log transformations. So I don't want to do more than you guys really need, but we will do some examples here. So first of all, what's the point? So the point of a log or a semi-log transformation is kind of to make the data more digestible. So let's look at an example. Let's say I wanted to graph y equal to, what's my example I've got here? 3 times 5 to the x. And I mean, I can certainly draw something like that, right? It's going to have an exponential shape. But if I start plotting some points, right? If I do, let's see, x and y. If x is 0, y is, I don't know why I'm writing y there. Y is going to be 3 times 5 to the 0, which is just 3 times 1, which is 3. If x is 1, y is going to be 3 times 5 to the first, which is 3 times 5 to 15. If x is 2, I get 3 times 5 squared. 3 times 25 is 75. If x is 3, I get 3 times 5 cubed. 5 cubed is 125. 3 times that's 375. And numbers get big real quick here, right? 5 to the 4th is 625 times 3 is 1875. So the point here is that this gets kind of out of control really quickly. Right? If I'm going to draw this, my scale has to be kind of huge, right? I mean, if I'm going to go up to, like, let's say this is 2000, and here are my x values of 1, 2, and 3, and 4, right? 0, I've got like right there. And then at 1, 15 is not much higher. And then at 2, I've got 75, which is maybe a tiny bit higher. 3, I've got 375, which is kind of like a quarter of the way up, maybe. So, right, it's just, it's hard to kind of see what's really happening on this regular graph where the x and the, well, I didn't even draw my x and y scale the same, right? I mean, if I draw my x and y scale really the same, these values all would have been smooshed in together, and it would have just looked like essentially kind of like a vertical line. You also, oh, I know what it was. That was the link I was doing here. If we look back at Desmos for a second, you can kind of see this graph. Sorry, I'm just deleting some things here. And we can see that 3 times 5 to the x. Oh, sorry, I don't know how to do times 5. Right, if we look at this for just 1 second, share, we can see, oh yeah, I mean, right, it's, we zoom out a little bit, it just gets, it doesn't seem very informative looking at that, right? It's like, okay, it's small and then it gets super big really fast. On the other hand, if we were to do a semi-log plot, it's actually going to help us kind of see the relationship between the variables better and to see how changes in one variable affect changes in the other variable. So we'll talk about semi-log first, and then we'll do log. So for semi-log, actually for either of them, for either log or semi-log, you're still going to start by taking the log of both sides. And when I say log, I don't mean natural log, I mean log base 10. So for these things, it's always log base 10. So if I'm starting with y equal to 3 times 5 to the x, I'm going to take the log base 10 of both sides. Okay. Now I'm going to try and simplify this. And this is where it's really important to be comfortable using the rules of logarithms. So on the right-hand side, log of something times something else, I can write this as log of 3 plus log of 5 to the x. And then I'm actually going to change the order of additions. I'm going to write this part first, the next one. So then I can also bring down the power and say this is, I'm going to say this part here is x times log of 5 plus log of 3. And now the reason we're wanting to do this, or that it's useful to do this here, is that this looks like a linear equation. If I replace log of y, I usually use a capital Y. So I'm replacing log of y with y, capital Y. I'm not replacing log of x. I don't have that with x. So that's why it's a semi-log. You're replacing half of the things with their log equivalent, but not the other thing. So this looks like the equation y equal to, I'm going to write it as log of 5 times x plus log of 3. Where this is looking like a linear equation. This is y equal to mx plus b. And so what we're going to see a lot, or maybe not a lot, but what I feel like we're going to see a lot, is that exponential equations like this, and this is exponential because you got 5 to the x. So exponential functions have semi-log graphs that are linear. Okay. So unfortunately, graphing these things is a bit challenging because you need semi-log graph paper. You can kind of make it yourself, but it's not the nicest. If you look on Canvas, I have posted a link to just some semi-log graph paper that you could print out if you have a printer. I don't know if you're actually able to really write on it particularly well, but let me show you what I've got here. So let's switch over to the other camera. Yeah, that is not super easy to see. Give me a second here. Sorry, I think there's too much light. Yeah, there we go. Okay, great. Now you can kind of see this. Okay, so hopefully that's somewhat readable. If you look here, so you see how we have these, sorry, can you guys see my cursor when I do this? You see my little arrow moving around? No, okay. So I'll just have to point over here. So you can see that, so each of these horizontal lines represent an increase in the value of our regular variable y. And I kind of switched my colors, unfortunately. Oh well. So if I'm looking at y equal to 3 to the 5x, right? This here is y equal to 1. This is y equal to 2, y equal to 3, 4, 5, 6, 7, 8, 9, all the way up to 10. But then once you get to 10, then you start increasing by 10s. So in this next kind of block, you go y equals 10, y equals 20, y equals 30, y equals 40, 50, 60, 70, 80, 90, all the way up to 100. And then in this next block, you go by hundreds. So every new kind of block, you end up increasing by a factor of 10 how much you're increasing by. Which makes sense. That's kind of how logarithms work, right? As you increase more and more to kind of the same output. So if I was going to try and graph y equal to 3 times 5 to the x on this semi-log graph paper, and it's semi-log again because the y values are not spaced out evenly, but the x values are spaced out evenly. So if I look at this, and I've already kind of pre-graphed this one because I was practicing earlier. So if I look right here, and I'm really just looking back at those values I've got, which are also over here. When x is 0, I get a y value of 3. When x is 1, I get a y value of 15, which is kind of halfway between 10 and 20. When I have x equal to 2, I have a y value of 75. So up here, 40, 50, 60, 70, 80. So it's just between 70 and 80 right there. And then when x is equal to 3, I have a y value of 375. So I go up to 100, 200, 300, 400, a little bit closer to 400 than 300. And so you can see that those points look like they fall in a straight line. And so when I graph them, they do. And then I'm going to try and actually draw the line. We'll see how we do here. Okay, that is our graph. So this is, yeah, let's actually do that. So let me see one thing. What do I want to say here? You can kind of go backwards as well, meaning the following. Sorry, I'm erasing. You guys will get my screen there. So let me stop sharing my screen. Yeah. Oh, I'm not sharing my screen. I'm stopping the, yeah. We go back to my other camera. All right, there we go. There's me again, all big. And let's see. Oops, that's not what I want to do. Sure. So, I think I just closed the one. Ah, I'm smart though. Oh, my last closed tab. Good, yeah. Sorry, I know this is a lot of me up close and personal. Come back. I had an example ready to go. Now it's gone. All right. So we can also kind of go backwards. And here's what I mean by that. So let's say we have the following information. When log of y is graphed as a function of x. This pen, I think this pen's dead. Or close enough to dead, but I don't want to use it. It's a good pen. A straight line results. Always this chair. I'm gonna have to figure out my chair situation. Maybe just move my board a little bit further to the right here. Straight line results with a slope of -4. And a log of y intercept of, what have I got here? +4. What is the original functional relationship? Well, here's what we're saying. So we're saying, well, I've got some straight line equation. So it's kind of like, if I underwrite like this, so y equal to mx plus b. I'm using a capital Y in the place of log of y and a lowercase x for regular x. Or, yeah. But you can also write like this, right? Log of y equals, so my slope was -4, and my log of y-intercept is +4. And this does make sense, right? If log of y is 0, then, sorry, if x is 0, apologies, then y will be 4, capital Y will be 4, or log of y will be 4, which is what we're saying. We have a log of y-intercept of +4. So the question is, what's the actual relationship, not between log of y and x, but between y and x? So what we're going to do is we're just going to solve for y. The way we're going to do this is we're going to raise both sides, we're going to write both sides as powers of 10. So say, okay, this is going to become 10 to the log of y equal to 10 to the -4x plus 4. Now, why would we do that? Well, what's 10 to the log of y? Oh, I see here, the new message. It's not just 1, although 1's not a bad guess. So here's something worth knowing. I bet, so let's go off to the side for a second. So I feel like you're all should be pretty confident that log base 10 of 10 to the y is y. For the same reason, all the stuff we did in the beginning of class today, right? Log base 2, 2, whatever. And so again, I don't write the base here because base 10 is like the common base. So the other thing that's true is, so when I say like, what's log base 10 of 1,000? What's the answer? 10 to what power equals 1,000? 10 to 10, 10. Anybody? Yeah, thank you. It is definitely 3 because 10 to the third equals 1,000. Okay, so when I look at 10 to the log base 10 of y, here's what this says. Log base 10 of y is the power you raise 10 to get it equal to y. But I'm raising 10 to that power, so it's going to equal y. Let me say it a different way, because I know that might not seem super duper clear. So I'll come back to this. We'll come back to it. Let's go to the other side real quick. So log base 10 of y. I'm going to say that's equal to x for a second. Now I'm going to rewrite this equation as an exponential equation. What's the base? I know you guys want to say words.
10.
Yeah, what's the power?
X.
What's it equal to?
Y.
Right, but look, x is all of this. So 10 to the log base 10 of y is equal to y. So that's what's going on there. So, and really the real kind of other answer to why this works is the way it does, both log 10 to the log base 10 of y equals y and log base 10 of 10 to the y equals y, is because these are inverse functions. 10 to the something and log base 10 of something, those are functions that undo each other. So if you compose them together, you should end up back where you started. So 10 to the log base 10 of y is equal to y. Exactly because this thing here is the power that you're supposed to raise 10 to end up getting what's inside there. But we're raising 10 to this power, so we're getting what's inside there. Okay. Sorry, I feel like it's really dark when I have these windows closed. But too bright for the document camera when they're open. So back to the other side. Yeah, that's what we're doing there. Pen on my hand. No fun. Pen on my hand. All right, so here's what we've got. 10 to the log of y, or log base 10 of y, is just y. And that's equal to, I'm going to break this up as 10 to the negative 4x times 10 to the 4th. Just using the additive law of exponents there. And then here's how we usually end up rewriting this. I'm going to write this as y equal to, I'm going to write the 10 to the 4th first, times, I'm going to write this as 10 to the negative 4th to the x power. That is usually the way this ends up getting written. Where'd you go? Yeah. Now you could simplify this a little bit further if you really wanted to, right? You could say this is y equal to, right? Since these numbers aren't too big, 10 to the 4th is just 10,000. And you could say 10 to the negative 4th is 1 over 10,000.
Does the order you write them in matter?
Say that one more time, sorry.
Does the order that you write them in matter? Like if I...
No, it doesn't really. The reason I'm writing it in this particular order is because when we write an exponential function, it's more commonplace to write the constant multiple first and then the base to the power of x after, but either order would be fine.
Okay.
But
Thank you.
the thing I really want to point out here is that this semi-log graph that was coming from a straight line ended up corresponding to an exponential function, which is something we said already, right? So exponential functions have semi-log graphs that are straight lines, and vice versa. Semi-log graphs that are straight lines come from exponential functions. Okay, how much time we got? 4-ish minutes. So let's look at one more example. sorry, where'd you go? Example. So the other types of functions that we usually look at are what are called power functions, which are really just polynomials, right? Like, well, not always polynomials because it could be x to the negative power. So we're looking at functions that look like some power of x. Not exponential, where x is the exponent, but power, where x is the base. So for example, y equal to 5x to the 4th. So we don't have a, I'm just trying to look at my watch, so it's not on right now. Like, oh, what time is it? Sorry. So for this one here, if you want to kind of see how this looks, we're still going to take the log of both sides. So the log of y equal to log of 5x to the 4th. And I'm going to use the same rules to break it apart. So I've got log of y equal to log of 5 plus log of x to the 4th. And then here, I'm going to write this as log of y equal to, I'm going to write this part first because we often write it first. And I'm going to bring the 4 that's a power out in front. So I'm going to get 4 times log of x plus log of 5. And now this is looking like y equal to mx plus b, where it's a log-log graph now because I'm replacing both log of y with some replacement y and log of x with some replacement x, right? It's different than the previous one because in the previous one, the previous one from a while ago, the x came out of the exponent down in front, wasn't inside the logarithm. Here that's not the case. So this is a log-log graph will end up being linear. And the gist here generally is that power functions like this, their log-log graphs are linear. Exponential functions like the previous two problems, their semi-log graphs are linear. If we want, we can take a look at this one. So yeah, let's go ahead and in the last couple minutes here, let's switch over to the, sorry, let's go back over to the document camera. Let's make it so you guys can see it. Hopefully that's not too bad. So here we have some log-log paper where both the x and the y axis are scaled in this weird logarithmic way. And so if I was going to try and graph this thing here, well, so the thing is when you're trying to graph something, you're still thinking about using the original values. So if I have y equal to 5x to the 4th, and let's start with y being bigger than or equal to 0. In fact, actually, let me see one thing here. I keep losing that page. Yeah. So that's, I meant to do x and y up there, sorry. So if x is 0, y is 0. If x is 1, y is 5. If x is 2, y is going to be 5 times 2 to the 4th is 80. If x is 3, y is going to be 3 to the 4th is 81 times 5 is like 405. So you're getting big real quick here. Now, if we graph this on the semi-log, sorry, not semi-log, the log-log graph paper here. So again, here's how our scale works, right? Here is x equal to 1. Here's x equal to 10, x equal to 100, x equal to 1,000. And over here, here's y equal to 1, y equal to 100. Sorry, to 10, woof, y equal to 100. And so if we start, we're out of time, sorry. So just if we start plotting things, right, if x is 1, y is going to be 1, 2, 3, 4, 5. If x is 2, y is going to be 80, which is 10, 20, 30, 40, 50, 60, 70, 80. There. And if x were to be 3, y would be 400, which looks like it's about 100, 200, 300, 400. And you can hopefully imagine, or see even, yeah, that's looking like a straight line. I mean, close. All right, so that's the idea with these log and semi-log graphs. We can definitely talk about this more on Wednesday. You don't have to do the polls. The polls are totally optional. So you don't find the quiz in the quiz section. You find the quiz in the assignment section. It's labeled as a quiz. And then you can click on the PDF and then you can write it yourself and then submit it in Gradescope. Also, if you guys make sure you fill out your attendance on this link. And then there was also one last thing. I know it's totally not important. Well, it's a little important. Where'd you go? This is totally unrelated, but I thought it was great. So I'm a fan of Hamilton the Musical. Here is a link to a video at about 8.5 minutes in. The whole cast gets on Zoom and sings the opening tune to a nice young girl. So it's like 8.5 minutes in. If you like Hamilton, or if you don't, give it a watch. All right, that's all I've got for you guys today. So take care, make sure you do the things, and let me know if you have any questions. I'll talk to you guys on Wednesday. You're all welcome. I'm going to end the meeting now because I got another meeting to go to. Bye.